All right, we are in week 3, and we are looking to cover modules 4 and 5. Since we got a head start on 4, that'll be pretty quick, just a few slides to finish off the wireless part. And then module 5 is hopefully a lot of review. Maybe the hexadecimal you didn't do so much, but we'll go over that. And basically, this is preparation for, what's coming in module, I think 7, the subnetting stuff. So IP addressing, subnetting. So when we get there, I'll go over, what these worksheets are and so forth. And I do not have you turning in any of the binary to decimal to hex to and back worksheets. Those are just for your own knowledge check, pretty much. The only thing I have you turning in regarding subnetting or related to subnetting this week are some subnetting problems. Well, the IP identification, little Quizlet, and that is the IP identification one is basically making sure that you haven't forgotten how to recognize Class A, Class B, Class C, default subnet mask, given an IP address with the subnet mask, what's the network ID of that address, all that stuff, because that will be important for subnetting. So that's what IP identification is. And the subnetting is pretty basic subnetting problems, the type that you should have covered in CNT140. And it's kind of, I'm giving you that here mostly to see, where you're at with it. And so that you see where you're at with subnetting. Because in this class, we cover subnetting, but, I find that people need to spend a lot of time on subnetting for the most part. And I don't want to spend too much time on basics of what you should have picked up in CNT 101. Doesn't mean I'll skip right through it, but I won't do as many practice problems as I normally do for CNT 101. We spend a good day and a half or so, sometimes 2 days on subnetting. And we just, we have to go on to the next level of subnetting, which is variable length subnetting. It's really not that much different. I hope that you'll see that. It's just a little bit harder, to wrap your head around if you're struggling with subnetting already. Variable length subnetting is just a little bit an additional step. So you must have some restriction on when these are published or what? Oh, okay. Yeah. Just tell me I can't unpublish them. So some people have already taken these, it looks like. So hopefully they've done well. I know that only because I can no longer unpublish anything that, like a quiz or an assignment that somebody's already done. And that's why the green check marks are grayed out. So at least one person is already forged ahead, hopefully successful. Okay, so that's what we're going to do today is the finish 4 and then talk about number systems and maybe, presuming if we have time, do a little bit of subnetting questions, problems. Okay, so wireless media. There's not a lot to the properties of wireless media because it's just, air. What you mostly have to know about wireless are, the standard numbers. And the most important one, the one that we care about from a LAN standpoint, a network, let's say an internetwork standpoint, is Wi-Fi, the 802.11 standards. And, you know, the 802.11 standards come in, you know, they had kind of peculiar numbering, or let's say lettering, 802.11a, B, there was no C or D, they jumped to N, and then AC and AX. And so, you know, the wireless standards people decided that's a little too complicated for most people. So we're just going to name them like Wi-Fi 5, 6, 7, which means the bigger the number, the presumably faster and newer the standard is. But you'll have to remember some, you know, the certification tests expect you to remember some of the properties of 802.11a and B and N. So you can't rely on just the simple nomenclature that they attach to those. And then these other standards, 802.15, just, you know, personal area network, think short range, Bluetooth, of course. WiMAX is more or less, well, in the United States, it's mostly defunct. No one uses it in their phones anymore. Sprint was the last company to use WiMAX in their phones for bringing, you know, 3G speeds. At the time, it was 3G speeds. Maybe it's 4G. Doesn't matter. It is used in some areas. I think you'll find it a little bit more in Europe as a method to bring high-speed internet to outlying areas, because you can beam the signal a long distance at a fairly fast speed. So you can sort of like light up an area, you know, a city block or something with a WiMAX signal. And if you have a WiMAX receiver, then you can, you know, access whatever the WiMAX signal is giving you access to. But it's not, you know, 5G for sure will wipe out WiMAX, because 5G does all that, you know, does it faster. Well, once they get 5G really going. Of course, by the time they do, there'll be a 6G. So, or we'll go to, you know, Elon's, you know, launching all those near Earth satellites, low Earth orbit, LEO satellites. And that's what it's for. It's for high speed network access. And it's not so high like the standard geosynchronous orbit satellites that are way up there and much bigger. There's a big latency, big delay between you and that satellite. So not ideal really for, certainly not for time sensitive applications. Low Earth orbit, on the other hand, you know, will potentially get rid of all the problems with standard cell, which is, you know, between two buildings, you don't get a signal, or you're, you know, behind a mountain because they're up there. There's no way to hide except maybe being in a tunnel or something. And then tunnels will start to put antennas on there, you know, like they do already for cell phone coverage inside tunnels. They'll grab low Earth orbit satellite stuff. But in any case, Zigbee is the you know, kind of an outlier here. As Zigbee is mostly a smart home or Internet of Things type wireless technology. Its biggest thing is very low power consumption. So you can put a Zigbee sensor out in the forest to collect whatever data on whatever.
Bigfoot.
Yeah, exactly. And, you know, with the, you know, minimal battery, and it can send it to a receiver potentially, you know, a long way away. And there's other similar technologies to Zigbee that are used for just that. You know, they might be able to go a couple of miles, some of them, but very low data rate. And, because high data rates, long distance takes a lot of power. And you want something, in a remote area where you don't want to run electrical lines to or have a big old monster battery, then some of these IoT, Internet of Things applications are a potential way to go. Okay, and then, wireless LAN, that's what we're going to focus on in the CCNA program. What do you need? An access point and a NIC. You really only need NICs because you can have a peer-to-peer type wireless network that doesn't require an access point. Basically, one of the machines or several of the machines potentially kind of act as the access point. But you don't see, those networks are really only used by somebody, group of people, and they don't, they want to be able to communicate with each other wirelessly, but they don't have an access point to set up. And so they just set up a ad hoc mode, is what it's called, ad hoc mode Wi-Fi network, where one of the machines, one of the laptops or whatever becomes the access point. But generally speaking, for LAN applications, for business, we have an access point, and then each end device has a NIC adapter. Okay. All right, so there's a packet tracer because packet tracer has some wireless devices, and you just go through the steps to make a wireless connection between a end device and an access point. And that was it for the remaining of module 4. I probably again skipped over some stuff that I just didn't think was, it was basically stuff that has already been covered in other classes or is not necessary for this class. So, this class really doesn't do a lot with wireless. So it's not something where we, spend a lot of time talking about. All right, so let's move on to 5. And again, I've cut out quite a bit of 5 because the basics of numbering systems and stuff, I hope you remember most of it. But we will do a quick review. Because really what I want to spend the time on is just going through some problems, some practice problems, and making sure everyone is good with it. All right, so binary and hex. Those are the two non-decimal number systems that you most have to have some familiarity with if you're going to be in computing as a profession, whether you're a programmer or an IT person. If you're an IT person, hex, you need to know hex because occasionally you're going to be looking at packets, protocol analyzer, and some of the data that might be in those packets, you're only going to see as hexadecimal numbers. That's how Wireshark displays information. They do try to decode it as much as possible, like they try to decode the headers of an Ethernet packet so that you could see the, in what looks like, just readable values, the source address, and destination addresses, both MAC and IP, and all the header information. They try to decode that so that you don't have to go and look up every single byte of a TCP header or an IP header to figure out what the value is. That's what a protocol analyzer is for. But they don't really analyze the data because they don't know what's in the data. That's not their job. What they try to do is take the hex and turn it into ASCII. So when you look at a Wireshark, I'll just bring that up. I'm sure you've seen it. Example. All right, so I think I just want Ethernet. I'm just going to capture, doesn't matter. So that's what's flying around our network without me really doing much of anything. But yeah, let me straighten these windows out. So they've changed the look of this. If I can find this yeah, I don't know what happened here. Usually you've got the, this is the decoded frame, this is the raw hex. And then usually, and maybe it's just a view option that somebody changed, or maybe this new version of Wireshark turned it off. But what I'm used to seeing is the hex here, and then the ASCII, which is essentially any printable characters that these hexadecimal values represent, you'll see here. And most of it's just gibberish. It doesn't mean anything to you. But occasionally you can see words and sentences and stuff like that in the ASCII. Should never bring up something to demo until I've run it myself. So I'm trying to figure out what has changed here. But I will maybe look at that later. Let's see if there's a quick view option. Anyway, I'll worry about that later. But well, it showed that the ASCII on the left screen, but not on what the heck's going on with that? So I move it over to my left to my other monitor, and it shows me the ASCII exactly where I expect it. So it must have something to do with the resolution. Huh. Must have something to do with the monitor resolution, why it's not wanting to display over on this monitor. Okay. Figure that out. Yeah. ASCII's sitting here looking at me. I move it over there so you can see it and you can't. Okay, so hex is somewhat important for you to be able to convert to a decimal or more even likely a binary value. Because when you look at data that's in the network or any type of raw data that you're looking at, especially if you're going to be in cybersecurity and you're going to have to do some forensic analysis of a hard drive that somebody tried to wipe, as you know, it's not really deleted unless you do a DoD type of wipe, and really better melt the darn thing down if you really want to be safe. But so, you may have to look at raw data, and then sometimes you may need to convert hex to binary. For example, in packets, TCP header and IP header both have fields that are just, they might call them flags or options or something like that. And it's just like 16 bits, or at most, they're mostly 16 bits, sometimes 8 bits field, which is 2 hexadecimal digits or 4 hexadecimal digits. And usually the way that data is represented or carried in a flag field or an options field is individual bits mean something. So bit 1 of the field might mean, for example, for TCP, that the SYN bit, the synchronized bit, is set. And maybe the second bit, bit 2 of the flags field in a TCP header means that the reset bit is set. And so things like that, while Wireshark, does decode those types of things. You may be in a situation where, you don't have the data decoded and you may have to decode it by hand. So that's why you need to be able to take a hex number, convert it to binary and vice versa. Okay, so you know what the binary numbering system is. We will deal primarily with groups of 8 bits, especially when we're talking about IP addressing. Each one of those groups of 8 bits is called a octet. Oct meaning 8. Each bit in an octet represents a power of 2 in terms of the decimal value that it represents. So you've seen this table, it's been up here forever. I don't know if the people in Zoom can see it, but it's actually had something I can put on people in Zoom. Shows that table. So something like that. That's we don't have the shorthand, the CIDR notation up there, but where you have each starting from the right-hand side of the octet, you have successive powers of 2. 2 to the 0, 2 to the 1, 2 squared, and so forth. And each bit represents one of those powers of 2. And that's how we convert, using a table like this, convert a binary number to a decimal number and vice versa. And we'll be putting that back up shortly. Okay, so in terms of an IP address, we have 4 octets strung together, separated by a dot. And that's why it's called dot notation. The octets for an IPv4 address are expressed in decimal. And so what we care about in terms of IP addressing is you will sometimes need to be able to convert the value of the decimal value of an octet to the binary value of the octet. So you can do your binary ANDing and so forth to figure out things like what's the network IP, the network address for this IP address, given its subnet mask. So that's why we need to be able to take a decimal IP address and turn it into, not doing that here, but take the decimal and turn it into the binary. We don't typically have to really take the entire 32 bits and convert it into binary for the purpose of subnetting. Generally speaking, you only need to convert the parts of the IP address to binary that are part of the subnetting problem. So usually, like the first octet is never subnet. So we're not gonna, you don't really need to convert that first octet to binary in subnetting problems. And in the CNT101 class, you probably didn't do much with dealing with the second octet either as part of the subnetting problem. Most of the problems in CNT101 focused on the third and the fourth octet as far as where the subnetting occurred. And occasionally you'll see, maybe in this class, us dealing with the second octet, but not that often. So anyway, that's why you need to be able to convert decimal to binary, is to be able to essentially do the binary ANDing to see what part of the address is network and what part of the address is host. Somebody have a question? Zoom? Talking. Okay. All right. So that's your IP address. So that video has converting from binary to, I think that's what it said. Yeah. IP address to binary and to decimal. So that this is the basically it's this table. The radix, ours I think looks better, or ours is more, we just have the power of 2, but the radix just means the base number, the numbering base that we're working with which is power of 2, base 2. Whereas decimal, what's the radix in the decimal number system? 10, base 10, right? And in hexadecimal, what's the radix? What's the base value? 16. 16. So that's all that means. The radix just is what's the base number we're working with, and the position in the number is also the power of that radix that we're using. So when you get a full octet, your leftmost bit in an octet is the 128th place, and the next one is 64th place, and so forth. So, and that's how we convert our decimal, or our binary to decimal, and we'll see same thing with decimal to binary. So I'm going to put back the table here. I'm just going to put a binary number in here. Actually, I'll write the binary number above the table. You put it in the table manually, and we'll see what you come up with as a. Okay, first, before you figure that out, is this an odd number or an even number?
Even. Oh, odd.
Why is it odd?
Wait, no.
Because the only odd number is
That's right.
the rightmost.
That's right.
The only odd place value is the rightmost. So if that is a 1, it's guaranteed to be an odd number because all the rest are evens. Okay, so that's kind of like your first check to see if you converted it correctly. If that last rightmost bit is a 1, then it better be an odd number when you've done the calculation. If the rightmost bit is a 0, it better be an even.
189.
189 we got? Anyone else come up with anything different? Okay, so hopefully you did it using the table and not a calculator, because if you want to take a cert test, you're not allowed to use a calculator in a cert test. Certainly not a binary to decimal calculator or vice versa. Some of them allow like an on-screen to do just arithmetic, but no cert test that I'm aware, at least not the networking ones, let you use a scientific calculator, either on screen or carried in with you. So you need to be able to do it without a calculator.
189.
So we just put this in our table, yeah, 189.
Thank you.
And we basically just add up all the columns that have a 1 in them. Right? 128 plus 0 plus 32 gives us 160, plus 16 gives us 176, plus 8, 184, plus 4 is 188, 0 plus 1 is 189. So it's as simple as arithmetic. If you remember the powers of 2 table, starting at 1, 2, 4, 8, 16, 32, 64, 128, and if I were you, just because it's useful for problems where you need to deal in more than 8 bits. Remember as many place values out to the left as you can. 256, 512, 1024, 2048, 4096, 8192. I can go up to 65536. And then after that, I gotta think. But that way you don't have to think. That's the point. Memorizing stuff, you know, and probably for the purposes of, you know, any of the certification tests, I wouldn't, you know, you're unlikely to get a problem that deals with more than 12 bits. You know, where you have to convert a 12-bit number, either decimal number to binary or vice versa. And so, you know, if you can do 4 more bits after this, 256, 512, 1024, 2048, that's probably enough for, you know, just memorizing what you might have problems relating to. Okay, so is everyone good with binary to decimal conversion? Anybody not? Because if you're not, there's a worksheet in Canvas in the week 3 at the, well, it's right above the assignments. I moved some of the files up right above assignments, and it's with a header called worksheets, and there's a binary to decimal conversion worksheet. And I don't think I posted the solution file for that, but I will. I just didn't. I ran out of time. So you know, you might, if you're a little uncomfortable with it, you might want to, you know, go over that worksheet until you are. Okay. I can undo everything, or just clear. I need to work more. haven't worked with whiteboard in a while. Okay, so then let's do a decimal to binary problem. So take 219 and convert that to binary, and I'll give you a few minutes or so and see what you come up with. Going from decimal to binary is what you have to do more often than the other way around. Okay. What do we have? Okay.
01011011.
Already I know that it starts with a 1.
I'm sorry,
11011011.
I had that.
Say it again.
I wrote that in.
11011011.
101. Say it again.
1
1.
011.
Good. All right. I'll take your word
110.
for it. But we'll do it. We'll do the problem. I don't know exactly how you do it, but this is the way I do it. So we start with our number 219, and we start over on the left, the very left-hand column. And of course, if our number was bigger than what, we'd have to extend this table another bit.
Or
219.
256.
255,
255.
right? Because 1, all, if all these were ones, it adds up to 255. So your number is bigger than 255, then you need to go over to the 256's place. And then if it's bigger than 512 or 511, you got to go over to the 512's place and so forth. But we're mostly going to be, working right here. with 86. So at least the way I do it, I go over to this first column and say, is that the value, is the place value 128, is it less than or equal to my number? And if the answer is yes, that's less than or equal to my number, then it gets a 1. And then I come over here and I subtract that place value from my original number, and I get 91. And then I come to the next column and ask the same question. 64 is less than or equal to 91, so we get a 1. And I think we're left with 27.
Yep.
And 32 less than or equal to 27? No, it is not, so we get a 0. We don't subtract anything, right? We just leave our number alone. And then is 16 less than or equal to 27? Yes. So we're going to subtract 16. I'll just do that in my head. Get 11 up here. Is 8 less than or equal to 11? Yes. Subtract, we get 3. Is 4 less than or equal? No. 2 less than or equal? Yes. Down to 1 less than or equal? Yes. Subtract 1 down to 0. So when you reach 0, you're done. And if all of your table has not been filled out, then what do? Like if I got to 0 from here, like if my number was 240, I would go 1, 1, 1, 1, and I would be down to 0. So what do I do now? Just fill it in with 0. The rest would be 0. And I used that example like 240 because that's the pattern, the binary pattern you'll see it with subnet masks. The last octet of a subnet mask, if it will either be 255 or 0, or it'll be one of these numbers, 128 or 12864. So it'll be 128 or 192 or 224 or 240 or 248 or 254, of course, or 255. And any value, any subnet mask value less than 255 will always be the last numbers or in the last octets. So you might get 255, 255, 240.0. But you'll never get something like 255, 255, 0, 240. You'll never see anything like that. Because in a subnet mask, all of the 1 bits are contiguous. You can have a string of 1 bits and then followed by a string of 0 or more. So if it's 255, it'll just be a big string of 1 bits. If it's anything less than 255, it'll be 0 or more 1 bits followed by 0 or more 0 bits. Okay, so you'll just, just to show you like that pattern, you'll see a lot. And be a lot of undoing, so I need to really figure out. I know there's an eraser. Let me see if that's faster.
I would just like to say I'm very proud of your penmanship progression.
I mean, my penmanship on this isn't much worse than it is on the whiteboard. I'm pretty bad. This makes it harder. I need to practice more. Okay, so if we had a number like a common subnet mask value like 255, 255, 255, 224. So the 224 is going to look like 1, 1, 1. Another common one, 240. 1. 248, etc. So that's kind of a pattern that you look for in binary pattern. You look for when you're converting the subnet mask, or at least the non-255 part of the subnet mask, to binary. That's a little better, I think. Okay, so good. Let's. So yeah, that's all this is doing some more practice converting binary to decimal and decimal to binary. So if anyone needs additional help with this, glad to help. Come in, before class, myself or Brendan or Alan, whoever's around, come in on Saturday, of course. There's tons of websites that probably explain it, pretty good as well. I'm sure that
Cert tests, do they tend to have like a graph like that, or is that something we're gonna have to memorize?
yeah. What I always tell people is if it's not in your head, then the last thing you do before you go into that cert test is study the table, and they give you a little a miniature whiteboard and a marker, because you're not allowed to have pen and paper and take it with you. So anything that you write stays with them. So as soon as you come in, if you know you're going to be taking like I think Net Plus has some of these problems with conversion, and certainly CCNA. So you just write the table down so before you forget it. So, but they don't give you that table in the actual test. Okay, so they're doing the exact same method as decimal to binaries we just did, I think. Yeah. Decimal number greater or equal to. Okay. So again, if you need more practice, I'm happy to help, but I don't think it's really something we need to. Much rather spend the time on the harder stuff, well, or at least the more advanced stuff. I won't say it's hard. Some stuff's hard for everybody, but the stuff that a lot of people have a problem with, which is the subnetting. But let's do hex. IPv6 addresses are expressed in hex. That's another reason to know hex a little bit. There's only a few places in an IPv6 address where you might need to decode the hex to binary. Some of the fields in the address have some meaning, primarily in things like multicast IPv6 addresses. So, knowing how to do hex to binary to hex, and sometimes even to decimal, there's really not that many reasons to convert hex to decimal or decimal to hex. You don't need to convert an IP address to hexadecimal. You don't need to convert a MAC address to decimal. IPv6. It's usually hex to binary or binary to hex. Doesn't hurt if you can convert it, to decimal, but it's not something that in practice is all that necessary. So what you need to know about hex is, since it's based on powers of 16, that means there's 16 digits to represent all numbers, just like decimal, powers of 10. There's 10 digits, 0 through 9, to represent all of our numbers. Binary, there's 2 digits, 0 and 1, to represent all of the possible values. So with hex, because they, you can't say 10, 1, 0, because you need an actual digit, a single character to represent each of the unique values that in the hexadecimal number system. Just like, with decimal, you go 0 through 9, and then you start reusing those digits to form bigger numbers, 1 0 for 10, 1 1 for 11, and so forth. So with hex, they just decided to use letters to represent the next values, 10, 11, 12, 13, 14, 15. So that's all you have to remember is A is 10 and F is 15, and the letters in between are the numbers in between when you're converting a hex number to decimal. Now, and really, to binary as well. Now with binary, the one thing you need to know about hex and binary is that it takes exactly 4 bits to represent all 16 hex digits, 0000 through 1111. And that is one of the nice things about, that's why hex is used in computing, is because it converts so nicely to binary and back. So any number, any hex number that I might put up here, I keep wanting to write in the whiteboard. Anything hex up there? I don't think I do. What is this? Yeah, that's for some subnetting problems. I'll just create a new one. Nothing. Somewhere in there, there's something with nothing on it whatsoever. Where to go? Oh, blank canvas. Okay, so any hexadecimal number, no matter how big or small, can easily be converted to binary as long as you can convert each digit to binary. So we'll just take that. Okay, so this is what, 3, 5, 6, 7 digit number. To convert a decimal number to binary, that's a 7-digit decimal number to binary, that would take a little bit of, it would take a while. Using the method that we just showed you with all the subtracting, and then you'd have to have a pretty big table for one thing. Your table would be, I don't know, how many bits? 7 digits. 7 digits is what, a maximum of 99 million? No, that'd be 9 million. Okay, so 7 decimal digits is as much as 9 million. That's up there around 26 bits or something like that. So a big table. This number here, this 7-digit hex number is much bigger than a 7-digit decimal number. I'm not sure. All I know is it's 4, 8, 12, 16, 20, 28 bits worth. So that can get pretty big. So all we have to do is take each individual hex digit and convert it to its 4-digit binary equivalent. And what is 2 in binary? Just give me four digits, 4 binary digits. What's that? 0010. You have to write real small. What's A? Remember, A is 10. So
1010.
1010.
B is.
B is 11 in decimal.
1011.
So 1011.
F is 15, so 4 is 2 is again 0010. And C is our 12, so
1100.
that's all there is to it. That converts, you could convert, pretty much any size hexadecimal number to binary much, much, much faster than you could have if this was a decimal number we need to convert to binary. Because you just each digit converts directly to 4 hex digits. I mean 4 binary.
Right.
Okay.
Now, if you were writing out in binary, do you need to separate it by each 4 hex tag, or what is it?
Say that again.
Written out all in one straight row, or does it need to be separated?
No, well, I mean, in practice or for any problems, you're never gonna have to convert this big of a number to binary, but no, I guess for reading, for ease of reading, you might, do 4 digits and keep a little bit of a space so that just for yourself, that each one represents a hex digit, but there isn't any like requirement to put any type of character in between these. You could either put them all together if that's what you wanted to do, or have a little space in between them, but everyone knows what you mean, what you're doing there with a hex to binary conversion. And then to convert the opposite way, I'll just do a simpler binary number. Make sure I don't do too many digits. Okay, so that's a 0. Wait, I'll rewrite that. All right, so go ahead and convert that to a hex value. 67.
What was that number you were talking about 2 million or millions? Where did that?
Well, what I was saying about that was this is a 7-digit hex number. A 7-digit decimal number would be the maximum value of a 7-digit hex decimal number could be 9,999,999. I was only throwing that out as a comparison of if we were trying to convert a decimal number of 7 digits, it would be a big number and it would take a lot of work to convert that to the binary equivalent. Simply because a decimal number, each digit does not correspond to very nicely to 4 binary. So you'd have to do successive subtractions, just like we did the small number. So it would take you a while to convert 9 million something decimal to hex, because you'd have to have a big long table of at least 20 some bits. I forgot, 24 to 26 bits. And you'd have to do all that subtraction and stuff like that. With hex, boom, it's easy. Each digit, 4 bits, and you're done. All right, so this is 67. So whenever you're doing binary conversion, binary to decimal, you just kind of draw a line to break it up into 4 digits, and then just 0110 in binary is 6, and 0111 in binary is 7. And so if I did another one, let's say, that's okay. So number like this, same idea, just kind of, whoops. Draw a line between 4 digits. you do these 4 digits, so it'd be 13, which is what in hex?
D.
D. No. D, yeah, you're right. D.
D.
D. D is 13. And this is just 5, so it's just 5.
Is there a reason in the binary? Is there a pattern to it? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0? Is there a pattern to that?
I was just writing ones and zeros down and
No, there's
wasn't paying attention to actually what I was writing
no,
down.
not that. And there's a graph here in the PowerPoint where it shows the decimal, binary, and hexadecimal.
Oh,
Yeah, is there a pattern that?
well, I mean, yeah. So when you're counting in binary, you just, it's kind of, I mean, it's hard to see, but it's the same idea as counting in decimal. When you count in decimal, and you get to the highest digit, what's the highest value digit?
Right?
9, right? So once you get, if you're counting, 1, 2, I should do it on this board. You're counting in decimal, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you want to keep going. You basically, and let's put 0 in there because 0 is really the first number that you start with. So once you get to 9, what do? You carry the 1, right? So like 9 plus 1, because that's what, when you're counting, you're just adding 1. So 9 plus 1, you do 0, carry the 1, and you get 10, 1, 0, right? And then 11, 12, 13, 14. Once you get to 19, you do the same thing. You go to 20. Well, with binary, it's no different. It's just that we're only talking about 2 digits. So you get to the first value, the highest number value. So if this was a 9, which is the highest decimal value, a 1 is the highest binary value. Well, when we want to get to 2, we add 1 to 1. We basically 0, carry the 1, and we get 1, 0. It's the exact same process as doing arithmetic in decimal. It's just that you're only dealing with 2 digits. So you get to your highest number really quickly. So we have 1, 0, that's our 2. And then we just start filling, adding 1. Add 1 to 1, 0, you get 1, 1, which is in decimal 3. Well, add 1 to this, and you get 0, 0, carry the 1, 1, 0, 0. 4. So it's the exact same process. So, if you say that, is there a pattern? Yeah. It's gonna always, when you're counting in binary, it's always gonna look just like this. Once you get, let's say 3 1s, then you're gonna go to 1 and followed by 3 zeros. And then you're just gonna start adding 1s again. Until, and what happens after 1, 1, 1, 1? 1, 0, 0, 0, 0, which would be 16. So, yeah, in that sense, there's a pattern.
Well, I guess, are we ever gonna be able to look at that? Just know, oh, 1, 0, 1, 1, that's
you should be able to look at this and say 1, 0, 1, 1 is 11 or in hex B. Now, you may still have to do, I mean, even I sometimes, if it's more than 4 digits, I have down pretty good. But if it's more than 5 digits, I still have to, think a second. Okay, 1, 2, 4, 8, 6, the 32's, 1, 2, 4, 8, the 16th place is the 5th digit. And, I have to do a little bit of arithmetic and, calculations in my head. But, I know this table in my head. If you don't, then you'll just have to, until you do, you would take that 1011 and plug it into the table. And come up with, oops, wrong one, but I've got it down here. So that 1011 you would plug into this table and say all the columns that have ones in them, I add. So 8, don't add the 4 because it's a 0. Add the 2, add the 1, gives me 11. And you do that often enough, and eventually you'll know that 1011 is 11.
I just made the connection of these 4 this to this table. and it
Okay.
makes sense now.
Okay, all right. Good. I'm glad you made that connection. Sometimes I assume that there's a connection, and sometimes I'm wrong, and you need to maybe point it out. Okay, so let's see what else. So does that pretty much explain hex to binary to hex? I think there's a worksheet and there might be a problem or two where you're going to do hex to decimal and vice versa. We're only going to work with up to 4, let's say, yeah, since we're sticking with octets, we'll only work with 2 hex digits, keep it pretty simple. So I'll do a couple examples of hex to decimal, from decimal to hex. It's basically the same idea as any other as doing binary, except you're working with powers of 16. So the numbers are much bigger, get much bigger, much faster. So, all right, so let's do hexadecimal first. And I'll do one that, looks hex. So I'll put some letters in there. So A3. Okay. So what you have to remember about hex is just like decimal. Remember with decimal, if I have a number 245, this is the ones place, the tens place, and the hundreds place, right? So we know 2 times 100 is 200, 4 times 10 is 40, 5 times 1 is 5. Add the 3 together, you get 245. Okay, you may not think that that's what you do, but you do that. You have to. It's the only way you can look at these 3 digits and come up with 245 is if you subconsciously, I'll give you, take the 2 and multiply times 100, take the 4 and multiply times 10, take the 5 and multiply times 1, and add the 3 together. That's the only way you could come up with that answer. Because if I change this, if I said a little 16 here, which means it's base 16, you're gonna have to do a whole lot different calculation. You're gonna have to do 2 times 16 cubed plus 4 times 16 squared plus 5 times 16. And, or 5 times 1, I'm sorry. 5 times, so I'm sorry, 5 times 1 plus 4 times 16 plus 2 times 16 squared. I gave it all the way up to 4 digits accidentally. And so you would see then that, you would have to do that arithmetic calculation to figure out the answer to that, which should tell you that you have to do the same thing when it's decimal. It's just that you've done it so many times in your life, you don't have to think about it. And that's the idea, that's the idea of what I said about configuring routers, doing binary decimal. Let's say the basic stuff. I won't say call it easy, because it's not easy for everyone. But the basic stuff you want to get down so well you don't have to think about it. If you had to, every time you saw a decimal number, go and do the 2 times 100, you'd look stupid, right? If you were, in a grocery store trying to figure that out with, money in your hand. And so, you know, you've done it so many times that you don't have to think that it's 2 times 100 plus 4 times 10 plus 5 times 1. Okay, but this you're gonna have to, because in hex, just like in decimal, this is always the and binary, the rightmost place is always the ones place. 16 to the zeros place. Anything raised to 0 is 1. So it's the ones place. And then move 1 over, and then this is the 16 to the ones place, which means the 16's place. So all we need to do to convert this to decimal is multiply 8 times 16 and 3 times 1 and add them together. A is 10. So this is a fairly easy one. So 10 times 16, 160, and 3 is 3. So 160, this would be 163 in decimal. And I'll just do the, you know, it's 16 times 10 plus 1. So that's our A, 10, and that's our 3. So we just, that's basically all you do. For 2 digits, it's pretty easy. The worst arithmetic you have to do is like 16 times 16. So, you know, 256 or whatever, 16 times 12, 192. So, you know, that's the most difficult arithmetic you have to do to convert a 2-digit hex to decimal is 16 times 0 through 16. And then, of course, 1 times 0 through 16. Add a 3rd digit, of course, and things get fun. So I'll make this a fairly small number. But what place is this?
16 squared.
16 squared's place, right? Just like it's the 10 squared's place if it was decimal. Or it would be the 2 squared's place if it was binary. So what decimal value does 16 squared have? And 56. Okay. So, you know, getting bigger numbers, we're gonna have to multiply 256 to up to 16. So that starts to get, or I'm gonna get my pen and paper out. 256 times 4, I can probably do in my head 1,024. But you know, like I said, since this is networking, we're dealing primarily with octets, 8 bits at a time. 2 hex digits represent 8 bits. So you're mostly just gonna have to deal with 2 digit hex numbers. And really, converting them to decimal, like I said, is not in practice, in computing, in all of computing that I've been involved in, programming, whatever, it's more converting each individual hex digit to its binary equivalent that you do. But, you know, we want you to be able to convert a 2-digit hex to the decimal equivalent as well.
So 16 would be 16 times 10, so 256 would be 256 times 100.
Yeah, well, okay, so since I made this a bigger number, now we've got 4A3. Now it becomes, well, I'll do the digit first. Becomes 4 times 256 plus A times 16 plus 3 times 1. So here's our hex digits, 4A and 3. So we just have to multiply them by their place value and add them all up. So 4 times 256 is 1,024. A, which is 10, times 16 is 160. And 3 times 1. So add those three together, you get what? 1,187, is that right? So 1,187. So, yeah, that, doing a 3-digit, like I said, just, you might want to do it just for, to see that you can, but once you get, multiplying 7, 8, 9, 10, 11, 12, 13 times 56, you might have to get out your calculator if you're not really quick with arithmetic, or your pen and paper. But usually, like I said, 2 digits is going to be enough. So I'll bring up that one. Let me see what the next slide is. That's just showing you IPv6, which I'll look at in a second. But let me bring up the worksheet for binary, hex to decimal, just to show you what is in that. And show you that, it's not that big a deal. Again, I'm not asking you to turn this in. This is just for your own, edification. If you feel comfortable with this, you don't have to bother doing them. But if you don't, then, I would go through the process just like we did. So just real quick, I'll give you 2 easy ones. You shouldn't have to go to the pen and paper for. What's 0F in decimal? 0F.
16.
Not 16. Remember F. Remember, there's 16 digits. 0 through F.
It's 15.
0 is your 16. So F is 15. So yeah, it's just 15. Yeah. And in binary, it would be what? 0, 0, 0, 0. I'll give you the first digit. 0, 0, 0, 0. What would be the last 4 digits? 1, 1, 1, 1, right? Because F is 1, 1, 1, 1. So that F being 1, 1, 1, 1 and FF being 1, 1, 1, 1, 1, 1, 1, 1, that's going to come up again. And it probably, when you were studying networking, you learned about broadcast addresses. Like, what's the broadcast address? All binary or all hexadecimal,
F.
or all 255s if it's an IP address. If it's a MAC address, it's all Fs. Well, the computer sees it a string of 1s. So from the computer standpoint, because computers don't read the numbers in and say, oh, that's an F, it just puts it in a register as whatever value it is. So from a computer standpoint, a broadcast address is all binary 1s. And that's going to be important, the all binary 1s part. And I think you've already seen this in some problems with subnetting. That's the broadcast address, right? So it doesn't matter if it's 8 binary 1s or 16 binary 1s in the IP address. If a broadcast address could be 3 binary 1s if the host field is only 3 bits long, right? So the idea that all binary 1s means broadcast, that all binary 1s specifically means in the host part of the address, which might be the last octet, the last 2 octets, or it might be the last 2 bits of the last octet. It could be you could have a broadcast address as small as 2 bits, a 1 and a 1. And we'll see that again when we do subnetting. So FF, what is it in decimal? The biggest number that you can represent with 8 bits, right? Because FF is the biggest hex number that you can represent with 2 digits. And what is that in decimal? What's the biggest number you can represent in decimal with 8 bits?
255.
255. Yeah. So FF is 255. So that one should just stick with you. FF is 255 because it's 8 bits. 2 hex digits. They're both F, which is the highest value hex digit. And so the highest value 8 bits in decimal is 255. In binary, it's 8 ones, 1111, 1111. All right, and then, these others, I think that's pretty close. It's close to what we just converted, but so do this if you're still need to, and I'll post the solution file so that you can check your work. But do these, and if you still having trouble, then you need probably to come in, open lab and work with somebody. All right, so IPv6 addresses, that's their kind of reasoning for talking about hex here. And you're gonna see in IPv6, a bunch of hexadecimal digits. It's gonna be well, it's 128 bits. Each hexadecimal digit is 4 bits. So how many hexadecimal digits are there in a IPv6 address? 4 into 128. So, they're big, long, ugly addresses. Thankfully, we don't really have to hardly ever deal with the last 64. This is the last 64. Because the last 64 bits of an IPv6 address is called the host identifier. And it usually just comes from the machine. The machine comes up with its own host portion of the address. Occasionally, as IT, people, since we're configuring devices, so on routers and some, switches sometimes, we will configure the IPv6 address and give it our own host address. But it's usually something real simple, like 1, 2, 3, 4, 5. There's no such thing as subnetting in the sense that we're used to with IPv4. So really, with IPv6, this address, this first 3 fields, as we'll call them, I don't think they ever came up with hextet, okay. I'll call them fields. Maybe I'll call them hextet sometimes, but I don't know. Sounds like I could get my words twisted and say something else. So these 3 fields of the IPv6 address, when you're talking about an IPv6 address that is going to be used by a computer to access, the internet and whatnot, that's going to be given to you by your ISP. It doesn't matter if you're a huge company like Microsoft or whatever, they're still going to get the first, well, maybe not. They might just get the first 32 bits from their ISP because they're so huge and they might need more than 16 bits of subnetting. But for most organizations, you'll get, if you say to your ISP, all right, we're ready to go IPv6, give us a global unicast prefix. What they'll typically give you is the first 48 bits. And then all you have to do as far as subnetting goes is assign each subnet some number in this 4th field, 0 to FFFFF. That's all it is. There's no subnet mask or dealing with converting things to binary. The subnetting in IPv6 is this field is mine, and each subnet, each, let's say, broadcast domain or VLAN, however you want to look at it in your network, I will assign a different number to. And same thing with the router interfaces. And the first number could be 0, and the second number could be 1 and 2. So pretty much, given that, every organization can create a network of 256 because we have 16 bits here, 2 to the 16th. No, what am I saying? Not 256. 16 bits, 65536, 65,536, subnets. And you don't even have to deal with subnet mask or do anything. You just decide, I'm going to assign building A, wing, floor 2, the value 2. Or maybe you might get clever and say it's building A, floor 2, so I'll make it A002. And as long as no other VLAN or subnet is assigned that, then you've got yourself a subnet. And so it's extremely simple. There is no real subnetting. The difficulty of IPv6 is going to be recognizing and understanding all of the different methods that IP addresses can be assigned to host, to end devices, and then all the different types of IPv6 packets, and a little bit the types of addresses that we'll be going into later. But that's going to be the difficulty of IPv6, is just remembering different types of multicast addresses and the different types of addresses, the global unicast and the link local addresses, and the third one that I always blank on the name, but it will come to me. So converting to decimal and binary, even with IPv6 addresses, isn't something that's going to be that common. But you should know how to do it for the rare case that it comes up where because of the fact that a certain bit is set in the first hextet, that means something about the packet or about the address. That's about the only thing you're going to have to remember. And there's only a few of those that you have to deal with. I don't even know if we get to that level of this class. All right, there was a video, we did this. All right, that's it for 5. Okay, so what I'd like to do now, and again, because I'm jumping ahead a little bit with as far as subnetting goes, because we have the time and we should make the best use of it. Basically to do a review of what I hope you know about subnetting. And you'll find out if you know it, I'll find out if you know it, and it'll give me a gauge as to how much do I have to spend on the basic subnetting versus variable length subnetting. So let's take a break. 10 after by that clock, so it gives you about 11 minutes to do whatever you need to do in your head. And then I'm just going to do some subnetting related stuff and some IP addressing. We'll start with just IP addressing stuff, like give you an IP address and tell me what the default subnet mask is, things like that. All right, Zoom people, about 11 minutes, we'll resume. It's got to be the specific password that it says in the lab to use. So where's the instruction?
Yeah, set that pass.
No, well, no, enables.
That's just a screenshot.
Oh, okay. Oh, this isn't the package. Okay. So the command has to be enabled, secret, and then whatever the lab says that you should use for the enabled secret password.
Are they able to open like a package?
Well, what does it say? It says secure access. So that instruction specifically says you should be using class as your privileged mode password. And when you say enable secret, it's that keyword secret that tells iOS to encrypt the password. To store it. So enable secret.
What's the difference between that and service password?
So service password encryption will encrypt all the other things that don't have a built-in encryption option. The enable command is the only password that has a built-in encryption option using the secret key. The password for lines and the BTYs, they are always in clear text and have a secret option. So you have to use the service password encryption, which encrypts all other passwords of the other ones. So if you do enable, yes. That's the password. Okay.
Is that what it's called? Is it mind games?
Yeah. It's supposed to help you
Wow, shit.
understand. Right there.
Oh.
Brilliant.
Just play it.
Yeah. It's just
Oh.
different types of lessons. And math and statistics and stuff like that. So there's.
Cool.
This is logic, but you can go. Village scientific.
Cool.
Solving problems. Skip that one. So we have to be 20.
Okay, let's just go over some of the question types that you'll expected to know on these little quizzes about IP addressing and subnetting for this week. So if I put an IP address down, say it's okay, so that's my IP address. What is the network address? What is the network ID for that IP address?
The network is the first two.
You said first two, what?
First two are touch.
The last one.
I'm sorry, you said 208.14, what? Yeah, I got a 208 and a 14, what else?
0.0.
Okay, .00. And so how do you get 208.14.00 as the network ID?
Because the subnet mask is 55255.
Okay,
That's the way I remember it.
Class C, okay, and what's the default subnet mask for Class C?
Oh, Class A, I'm sorry, then it's 208.
Right, so does anyone want to change their mind about what the
Yeah, it's
network ID is?
208.4.2.
Okay, so that's the first thing is, when I first asked the question, somebody should have come up and said, you can't answer the question. Because the only way you know what the network ID is if you have the subnet mask.
That's right.
And hopefully you learn that just because it's a Class C, well, that's the default subnet mask. That doesn't mean that that's every address that is 208.14.12 dot something is going to necessarily use that /24 or 255.205.250 subnet mask. So the next reasonable thing to assume, since I didn't tell you any other information, was to use the default, which means you have to know what class of address it is. How do you know what class an address is? Just by looking at it.
First octet.
First octet, right? So 0 through what is a class A? There's 3 classes that we can assign to host devices. So 0 through what is a class A?
127.
127. Right. And class B goes from, so let me write those down. A 0 through 127. B what?
Or 128 to
91. C
192 to 223.
220. Okay, so this is the first thing that you're going to have to know. First off, it's the first octet that determines that. And secondly, the range. Now, there is, if you prefer, you can actually look at the first 3 bits of the address of the first octet, and a particular pattern of the first 3 bits will tell you the class as well. So in a class A, the first 3 bits are always, well, let's say the first, let's look at the first, we don't really care so much about the third one. It's going to be, well, 0, 0 through 0. Okay, and a class B, the first 3 bits will be a 1, 0. Or, yeah, it's really the first bit or the first 2 bits. So class B, to get values 128 through 191, you'll always have the first 2 bits be 1, 0. 1 followed by 7 zeros is 128. 1, and then to get up to 191, you'll only have the 32, the 16, the 8, the 4, the 2, or the 1 bit. So that's why 1, 0 is the pattern for the class B. And then a class C, the first 2 bits will always look like that. So really, looking back at a class A, 0, 0 or 0, 1 for the first 2 bits tells you, actually, with a class A, all you have to do is look at the first bit, because B and C, the first bit is a 1. So with class A, you just have to look at the first bit, and if it's a 0, then it's a class A. Class B, the first 2 bits have to be 1, 0. Class C, the first 2 bits have to be 1, 1. And that's how the computer figures it out. The computer does not, like when you know how when you type in an IP address into Windows, into the network interface settings, and you type in an address and then you tab down to the subnet mask and it's already fills it in for you with the default. It's not because it does a comparison and sees if it's in the range 0 to 127, so it must be a 255.000. Computers are much smarter than that. They just look at the bits that matter, because that's the fastest way to do it. So the computer is just going to look at the first 2, the first bit. If it's a 0, then it's got to be class A. If it's not a 0, then it looks at the first 2 bits. And if it's 1, 0, it's got to be a B. 1, 1, if it's got to be a C. And if it's 1, 1, 1, then it's got to be a D. But we don't assign class D addresses to computers ever, only A, B, and C. So that's the other thing. The first octet, it can't be 0. 0 is reserved. So the first octet has to be in the value of 1 to 223 in order for it to be a valid IP address to assign to a computer. You know, a multicast address is a valid address, but not to assign to an individual machine. So it's got to be in range 1 to 223. Okay, so you know that the first octet is the most important in terms of determining the class. And a class A has a 255.0.0.0 subnet mask. A B has a 255.255. So A is going to be 5, 0.0. And what is the shorthand for 255.0.0.0? In other words, the site, what we call the CIDR notation or the prefix notation. The class B is going to have a default of, I mean, I almost don't like talking about classful addresses because when it comes to subnetting, you just ignore class. However, there are certain situations when you're configuring routers where they're going to talk about classful. That it'll default and summarize on classful boundaries and things like that. And you have to understand kind of what that means. But too many people get hung up on if it looks like a class C, then the subnet mask must be this, and that's not the case. All right, and what's the CIDR or prefix notation? So what do those numbers mean, the 8 and the 16 and the 24?
It's the network ID. The network ID.
It's the number of network bits,
Right,
which determines the network ID. So this just means /8 means that if I just wrote the IP address /8, then you would know, not that it's a class A. Remember, a subnet mask doesn't make a particular address, a particular class.
Huh.
A class is, the address is a class, whatever class it is based on that first octet. But I can take this address, 92 and 68 and 1, and assign it to my computer with this subnet mask. Nothing wrong with that. It doesn't change this to being a class C. It just means that instead of the first 24 bits, which this is a class, this is a class C address, but the whole idea of CIDR, the C in CIDR means what? Classless interdomain routing. So the classless means that we're just going to ignore the class and we can use whatever darn subnet mask we want if that fits our needs for our network. So if I do this, that means that I've changed the network ID from 192.168.10.0 to 192.168.0.0. And I can absolutely do that, and the computer won't complain. If it was Windows, it would automatically fill in the third 255, but I just change it back to a 0, and we're all good. Yeah.
Do they only use CIDR in specific circumstances, or is that pretty common?
Using CIDR, you mean the notation?
Well, just the classless in general, like.
No, it's pretty much the way that all networking is done. Now, there are some old protocols running around out there that still have an attachment to classes, like the RIP routing protocol. which we don't even really, we mention it, but we don't study it. I think we go a little bit into very minor detail of RIP version 2, which got away from the class stuff. But the RIP routing protocol, which is still available on all the routers, you can say router RIP and it'll work. But it bases all of its routing based on classful addresses. And so when you start to do subnetting in a RIP routed network, you can really screw yourself up because it does some things that can break your network depending on how you've configured and where you put your subnets and stuff in relation to the router interfaces. So you don't ever really want to use RIP. If you're going to use RIP, which is the easiest to configure and simplest operating routing protocol, use RIP version 2, which basically means you say router RIP on a Cisco router, you say router RIP, enter version 2, type version 2, and now it's version 2. That's about all there is to it. So anyway, like I said, there's a few protocols, older ones that are kind of attached to classful addresses, but by and large, you kind of ignore class when you're talking about subnetting. Now, since certification tests still expect you to know this stuff, the default subnet mask, and given IP address, what its default subnet mask is based on its class, that's why we still have to teach it. But when we subnet, just get the idea of class out of your mind. Unless I say, here's your address, and the subnet mask that goes with it is the default based on the class of the address. That's the only time that I'll even mention class when we're doing subnetting. Okay, so the slash number just corresponds to the number of bits in the IP address that are part of the network ID. So the first 8 bits, if it were a /8, or had that subnet mask. The first 16 bits, if it were 255.255.0.0 subnet mask. The first 24 bits will be the network ID if it's a 255.255.255.0 subnet mask. And you understand how the 24 corresponds to this subnet mask, right? Because there's 8 ones, 8 to make 255, 8 binary ones to make that 255, and 8 binary ones to make that 255, to give you 24.
It could be 27 though, or?
Yeah, we'll see that it could be 25, 26, 27 when we start subnetting. Yep. So, okay, so let's look at another type of question. All right, so given an address with class C subnet mask. So again, there are a few questions in this quiz you'll take that say things like, how many hosts are there in a class C network? So class C network has a subnet mask that looks like this. So how many hosts can you have in that network? 254, and you got that by what?
Was the last octet.
You need to reserve the network
broadcast.
address and the broadcast address, so you only have 254 to 256 available.
Right. So the fact that the network ID is the first 24 bits,
Right.
that means the host address is the last octet. It's 8 bits. So you have 8 bits of host, and the formula is 2 to the n meaning number of bits. So 2 to the 8 gives us 256, but you got to subtract 2 addresses from that. And those are the network ID addresses, in other words, the 0. So let me just put an IP address to go with this. Okay, so with that subnet mask, our network ID would look something like that. Okay, well, this octet can have values 0 through 255, right? In binary, the 0 value, of course, looks like this. And the 255, which is the largest number we can have in that octet, is going to look like that. So these two addresses are excluded from being assigned to hosts because this is the same as, so 12.0 is a valid number, a valid IP number, but you can't assign it to a host because it's also the network ID. So you can't use the network ID. And the reason you can't use this is because
Broadcast.
it's the broadcast. So since 255 looks like this in binary, all binary ones, if the entire host part of the address is binary ones, all 8 of them in this case, that is the broadcast address. You can't use that to assign to a computer. So we have 0 through 255, which is 256 numbers, but we can't use the very first one, the 0, or the very last one, the broadcast, the 255.
This might be a weird one. I'm trying to think how to. So if it was a class B, you could use the last 2 as hosts.
Mhm.
And then, so in that case, would you still only have one broadcast and one, or would it be like, so like
No,
that
no,
12?
you'd still just have one broadcast. So let me, if I did this, if I said, completely change, well, let me, I completely change this up and said, this is /16, which means for a subnet mask, looks like this. Okay, then could I assign this address to a computer? 199.14.12.0, if I use this subnet mask, could I assign this to a computer?
Sure.
Absolutely, because the rule is you can't assign the network ID. Well, the network ID for this would be 199.14.0.0 because the last 2 octets are the host, because the first 2 are the network.
That's for the.
So this is just some address, you know, I don't know this, how many addresses in, it's like 1,000 something address in the 199.14 network. And then, you know, in order to make that the broadcast, like if I did ask the same question, can I use this address and assign it to a computer? Can I assign that to a computer?
Yeah.
Yeah, because again, since the network ID is 16, that means this, the 3rd and the 4th are the host. And the rule is you can't assign when the host is all zeros. So that would have had to have been 0 for it to be not usable. Or you can't use it when the host, entire host field, 2 octets, is all binary ones. Well, the last one's binary ones, but the 3rd octet clearly isn't. So it's a perfectly fine address. As long as the subnet mask is this. If it were 255.255.255.0, then we go back to the original, no, you can't use that because it's the broadcast. So it all depends on, you know, how many bits, what part, you know, how many bits are network, how many bits are host. If all of the host addresses are 0, can't use it. If all of them are 1, binary 1, you can't, it's the broadcast, you can't use it. But if only one of them is not 1 or not 0, then it's perfectly fine address.
So A and B are for just massive networks overall.
Yeah, it's a real big network, 65,534 hosts that you could put on a class B single broadcast domain, which you'd never want to build because 65,000 computers, all you'd get is broadcasts. That's all you get. I mean, you saw when I brought up Wireshark, most of those packets that you saw were broadcasts or multicast, which are treated the same as broadcast by our switches. So it's, you know, and I wasn't doing anything. And probably most of you weren't doing much and just packets flying. That's what our networks are today. They're just constantly talking to each other, the devices, make sure they're still alive, whatever. So anyway, so that's the, that's a big takeaway is when you're asked about, can you use this for host assignment? Now, one of the things that I found with this quiz, I thought I had actually changed it, but I'll tell you verbally. So you're gonna get some questions that say which IP address can't be used for a host assignment. You have to, if it doesn't give you the prefix value or the subnet mask, you have to assume that the default for the class address. Okay, so that's why you need to know the ranges of the class addresses. So again, I'm not a lot about this kind of questions, but it's basically, testing you on, do you remember the class of address so that you remember the default subnet mask. So you'll get questions like that. There's also other addresses, like, remember we said class A was 0 to 127. Well, you can't use that. That can't be your first octet. What else can't you use when assigning to a host? Is there any other address in this class A range that you can't use to assign to a computer?
168.
That's not part of the class A, but
Isn't there a default address?
well, you
10 to
in the
10.
first octet for a class A, can you use 1 through 127 when you're assigning a computer an address to a host, to a device? No, you can't use 127. Why?
Oh, right, because that's the last one. You can't use the
That's
first one and the last.
I
one.
bet.
Address.
I bet, and I can just guess, give me any address, random address that starts with 127, and I bet it replies. So you might have thought, oh, I memorized that address and I know that that's on my network, right? Give me, if I try any address, it's random. So why can I just type in ping any address that starts with 127 and I get a reply?
It's a broadcast address.
It's the loopback. And it's, most people think of it as 127.0.0.1 because that's what has typically been defined as local host. But anything that begins with 127, as long as it's not 0000 or 255.255.255, then it is the loopback address. And the local computer is responding to those pings. It's not even going out the network. It's not even touching the NIC. It's just directly going up to the IP stack to say, is the IP stack alive and well? So any address that begins with 127 is the loopback and can't be used to assign you. Okay. Oh, your private addresses. Do you remember your private address range?
Yeah, that's what I was just saying, isn't it 10 to 10.255?
So each class has a range of private addresses. And so you need to know those. What is it for A?
10 to 10.255.
10 dot whatever. /A. Okay, so anything that starts with 10 in the first octet is a private address. Class B,
It says 2.16.
anything 172.16 through 172.31 is a private. Class B and Class C,
2.16.
anything 192.168 is a private IP address, which just basically means what? What is special about private IP addresses?
They can't be
For
routed
like
to the internet.
businesses.
Can't be routed on the internet. Which means, since they can't be routed on the internet, that means any organization that has a router between them and the internet, which everyone has to have that, can use any of these addresses for their private network. And then what happens, you're sitting at home and you probably have a 192.168.1 address for all your computers and your TV, smart TVs and everything else. How are they getting out to the internet? What happens?
Doesn't it convert it to a usable address?
What's that?
I said, I thought it converted it to a usable address.
Yeah, exactly. It converts it, or the term is translate, network address translation. So every time that you try to access the internet, same goes for in here, because we're using 172.31, which is part of the Class B range of private. Anytime that your computer is accessing the internet in here, at home, wherever, a router somewhere, usually it's one of the last ones before, you know, you're out into the outside world, will take your packet and convert the source address from this private address into some public address and keeps track of it in a table. So it knows to convert it back when the reply comes back.
Is the address going out the address of the router or of the actual PC?
No, it'll be the address that the router has.
Okay.
Some address that the router has.
So
It may not, for home networks, your typical home Wi-Fi router, it will be the router's address that it got from the ISP.
because the
So the-
router renews leases, doesn't it?
Yeah, rude news, but those, yeah, from the outside world,
Yeah.
yeah.
And so can it be-
It'll get a different public address periodically, and when it does, though, you know, the translations just get changed.
Okay.
So, for your home router, Wi-Fi router, it's doing the translation using whatever address your ISP is assigned to that connection of your router, the connection on your Wi-Fi router that says internet.
Okay, so it's not entirely randomized, it's based upon the ISP.
Yeah, the ISP gives you an address and all of the communication that goes out gets translated using that public address. But the router keeps track of all the conversations in a table. So when the reply comes back based on another number, the port number of the conversation, it knows who to send the reply to inside this. So anyway, now in bigger networks, you may not use the router's actual address. You can have a bank, let's say a pool of public addresses that your ISP is allotted to you, because like Yale College is too big to have just one address that everything gets translated to, because translation tables would get huge, you know, and they'd have to search based on just one address. So we've got, I don't know, a bank of 3 or 4, at least maybe a dozen, so that the translation tables are a little bit easier to search.
So that leads to the second question. Those tables that you're getting, those banks, are they allotted per building or is it just randomized?
Oh, yeah, it's just random. It's like, you know, whatever address is up next is what's used by the router. Okay, so those, you know, private addresses is something you need to know. Classes of address. Most of this is about address classes and default subnet masks. And knowing which part of the address is the host, which part is network. So I think we've pretty much covered that. All right, so just real quick, since I know people are getting tired, I'll just look at as much as I can the basic subnetting. We may, well, if you want to go over more subnetting on Wednesday, I won't be here, but Brendan will be. We were just going to do the labs from last week, the module 2 labs, but that probably won't take, you know, all that long. There's only 2 of them. So it might be time for you to, ask him, so he's pretty good with subnetting.
Yeah.
So he'll be able to help. But let me just give you an idea of what we're talking about. Okay, so at its most basic, the most basic type of subnetting problem is going to be, well, let me bring up that table actually, because I think that'll probably cover most of what we All right, so here we have a bunch of IP addresses along with their prefix. So and what you probably want to do, you don't necessarily have to if you're already pretty good at this, is take the prefix and turn it into what the subnet mask looks like. So that for some people, that's easier to visualize what the network address is and the broadcast and all that. But let's start with the easy stuff. And that is the number of hosts. The easiest thing here is the number of host bits. So for this first problem, here, I need to do it on my white thing so that Zoom people can see. So with this first problem, this first problem, 172.49.336.28. Okay, so the important thing here is the /28, because it doesn't really matter what this number is, because most of the answers will be close to the same thing no matter what you've got here. The /28 is what's key. So first thing to ask is number of host bits. So how many host bits are there? There's 4 host bits, right? Because if there's 28 network bits, as specified by /28, then there's only 4 left because we've got a 32-bit address. So how many hosts per network do we have?
16.
1, 2, 3, yeah, 16.
How many hosts can we actually put on that network? There's 16 addresses.
Oh.
We can only put 4.
Oh,
we can
right.
only use 14 of them, right? Because can't use the network ID address, can't use the broadcast. So that brings us to that. So what's the network address? We know that 172.49.3 is going to be part of that. How do we know that? Is because /28 is bigger than 24. And so 24 is all the way through the first 3 octets.
Right.
So
add
the first 3 octets have to be of the network address have to be the first 3 octets of our address. And so now all we have to do is figure out how many bits are we into the 4th octet, and what does where does 36 fall in terms of the subnets that we've got.
We're 4 bits in, and that would leave us with 4 bits, right?
Yeah. So we've got 4 bits left of host. So this is where you most people want to do some binary with this. If you've been doing a lot of problems, you can probably do it in your head, because I know.
So that's where you're doing the 8 and 4 and 2 and 1.
Well, let's just
So that's 4.
let's bring. I've got the table here. That's good. So let's just look at what that 4th octet looks like in the subnet mask. We know that it's going to be 255, 255, 255, right? Because 24 gives us, if it's just /24, that'd be 255, 255, 255. So it's more than 24. So we know that there's 4 bits of network ID in the last octet.
One
So we just put our 4 bits down in our table,
240.
Yeah.
and there's our host bits, right? Okay, so the thing to do now, the easiest thing to do, I mean, you could go and do all the binary ANDing and it would tell you the network address. And I recommend that if you haven't done that as an exercise, that you should, just so that you kind of understand the process. But let's say the quick way to figure out, what we have to figure out is what network
240.
is that 36 in? And the way that you figure that out is you look at the last octet of your the last non-zero octet of your subnet mask, which is going to be the 4th octet. And you look at the rightmost 1 bit. So this is the last octet, which will be what? Again, I'm doing it, I keep forgetting about Zoom people. So we're going to have a value, and the value really doesn't matter, but we're going to have a value of 240. That will be our subnet mask, or the 4th octet value of our subnet mask. But what we care about is that what subnet is the 36 in. And the way to figure that out is say, all right, the rightmost 1 bit is always the increment that our subnets are based on. So subnet numbers, subnet IDs always start with .0. And then they increment from there. They might be like if it was a class C, it would be, .1, .2, .3, .4, .5, because the rightmost bit is the 1 bit. But in this case, the rightmost bit is the 16 bit. So our subnet increments are going to be by 16s.
You don't have to subtract the 2.
We don't have to subtract anything here.
Okay, cool.
We did that for the host.
Yeah.
So we look at that 16 and we say that is the increment for our subnets. We don't have to even care what the original subnet mask was or anything. All we care about is what the subnet mask is now. And that subnet mask, the rightmost bit is the 16 bit. Based on, 25, 26, 27, the 28 bit. So that is so this 172.49.3 network was subnetted like this, 172.49.3.0. That was the very first subnet. And then the next subnet that was by taking that /28, the next subnet was 3.16, right? And then 172.3.32. And then 172.49.3.48, and so forth and so on. It really, it doesn't matter, what all the subnets are for this type of problem, because we don't know what the original subnet mask was before we changed it. It could have been 205.205.0.0, could have been 255.255.255.0. It doesn't really matter. We do know what it is now, and that tells me that these are the subnet boundaries, the 0 through 15, 16 through 31, 32 through 47, 48 through 63, etc. So the network address is for 36. What network is 36 in? It's got to be between, one of these subnet values.
Right, 32 and
It'll be in the 32 network, right? So 32 is the network ID. 33, 34, 35, 36 is this host address. So the network address is basically the network ID for any given address is the subnet address less than the value of the host address. So it's going to be 32. And then the broadcast. Now, the broadcast, since we know that we're counting by 16, 0, 16, 32, 48, Well, the rule, the quick way to figure out the broadcast address is just to look at the next network address and subtract 1. Because network address can't be broadcast address. It's the network address has all the host bits being 0. The broadcast address has all the host bits being binary 1, and I'll prove it to you. So if the network ID in binary is 32, that is going to be 0, the network address 00, 10, 0, 0. Right? And here's our delimiter between our network and our host, right? Because 28 bits means 4 bits in this 4th octet are network ID, and the last 4 are host. So here's a little line. This is 32. This is our network in binary. So all we have to do to figure out the broadcast is make all those zeros in the network address 1s. And so 0, 0, 1, 0, 1, 1, 1, 1. Convert that to binary, I mean decimal, and you've got your broadcast. 32
30.
plus
52 plus
8 is 40, plus 4 is 44, plus 2 is 46, 47.
7.
So that's going to be, I'm just going to write the last octet. So dot 47 is our broadcast. Again, the cheat way, or it's not cheating, it's just understanding the patterns and using them, is to look at your next subnet. So if you know your network ID, look at the next one based on our increment and subtract 1, and that's always going to be your broadcast. Your last, your usable range of addresses will be 33 through 46, because the first usable address is always 1 more than the network address. The last usable address is always 1 more than the broadcast, or 1 less than the broadcast address.
And if you know your number of hosts, you just add that and you would have your.
Yeah, you also know the number of hosts, right? So add your 14 to your 32, that gives you your last host address. Yeah. So, okay, so that's, this is something that I don't know if you went over this table in CNT 101. Part of the assignment, it's part of at least when I last taught it, I included this as part of the subnetting stuff, but it's, if you can do this table, then you can probably do most of the questions in the subnetting quiz.
Cool.
So, but I'll ask a few of the questions a little differently. So let's say, that there was 4 host bits here and that it gave you 14 host bits. So what if I asked you the opposite question? And let's say I need 62 addresses for each of my subnets, 62 host addresses for each of my subnets. How many host bits do I need to be able to make that work? I need 62 host bits. 62 IP addresses per subnet. How many host bits? Yes, 6. So that's, that's one of the type of questions that you might get. Or based on, if you have 6 host addresses, how many hosts per network? You got to do 2 to the 6 minus 2, which will give you 62, right? 2 to the 6 is 64, but you always got to subtract the network and the broadcast. Other ways questions might be asked. Okay, just doing the opposite to make sure that this is understood. How many bits do I need? Like if I start off with a 255.255.255.0 subnet mask, and I need to subnet that and make 32 subnets. How many bits do I need to reallocate from the host to the network ID? 5, right. So remember, when we're talking about number of bits, you only subtract the 2 when we're talking about host bits. When it's subnet, when you're saying how many bits do I need to create, 16 subnets, you only subtract the 2, the network ID and the broadcast when we're talking about host per network, host bits. When we're talking about subnet bits, it's just 2 to the n. So if I say I need 128 subnets, then whatever 2 to the 7 in this case will give me 128 subnets.
You got 14, I know you subtracted 2 from 16, but how you got 16? It's not that you added the value of the first 4 bits. That's how you got 16.
Oh, this 16?
No, well, like 1, 2, 4, 8, because that's the 4.
Well, this is just the powers of 2 table. 1, 2, 4, 8, 16, 32, 16. So 2 to the 0 through 2 to the 7.
So like the number, so
He's asking-
CIDR is 28, and that told us that the number of host bits is 4. I understand that, but then from that to get the number of host network, you said that we're adding 1 plus 2 plus 4 plus 8.
To figure out the number of
Host network.
hosts per network.
How did
I see, yeah, more or less you are, except that's gonna give you 15. So you do have 4 bits, and you could say, okay, but remember that this basically starts at 1, right? So you got, there's 15, the 4 bits gives you values 0 through 15, which is 16 values. That's where we get the 16 from. And then we subtract the 2 to get the 14. Okay, so when just adding these up, 15 is the biggest number you can get, but there's 16 values that can be created with these 4 bits, 0 through 15. Okay, and that is confusing for some people. There's like, well, I only see 15 here. How is 2 to the 4 16? Because the value, the highest number you can create with 4 bits is 15, but there's 16, just like 0 through 9, there's not 9 values, there's 10, because there's the 0. So there's 10 values that you can create with a single decimal digit, 0 through 9.
So 2 to the 5th would come up with 31, and you just add 1 to that? Say-
Well, but 2 to the 5th is actually 32, 5 bits. Because remember, we start with the 0 bit.
Okay,
So it's just like, in decimal, 10 cubed. 10 cubed, you might think, is going to give you a 3-digit number, right? It's not, it's 1,000. Because
times 10 times 10.
you have 0, you can create 1,000 values with 3 digits, 0 through 9999, which gives you a total of 1,000. So it's kind of this same idea, except with only powers of 2. Okay, so let's do one more. Let me pick which one. Let's do 19. The third one, 9.12.67.120/19. So first thing is, how many host bits do we have?
13.
Yeah, 13 host bits. Here's where you're gonna have to do a little more than 2 to the 8th in your calculation. So 2 to the 13th, and again, I don't know it off the top of my head, I just use my fingers. I know that 2 to the 8th is 256, so 2 to the 9th is 512, 1024,
8,000
10.
192.
12, 10, 20, 2,048, 4,096, 8,192. Is that what you said? Yeah. So 8,190, what? How many hosts?
90.
Nine.
8,190.
Always subtract 2. So we got 8,190 hosts per network. We have 13 host bits. And where is our, okay, so we know that our subnet mask is going to be 255, 255. And then the third octet is where, you know, the subnetting occurs. So 255, 255, and then 17, 18, 19.
128. Oh,
Okay, so that's in binary what our subnet mask looks like in the third octet. So we end up with a /19, 255, 255, 224.0. Okay,
So that,
so, yeah,
so that 8,000, you're going 2 to the 13th power? That's how you're
Yep.
getting 8,000? Okay,
Yep. 2 to the 13th power to get 8,192 and subtract the 2.
gotcha.
Okay, so remember that this is what our subnet mask looks like. So our network ID actually exists in the third octet, you know, the non-zero part of our network ID. So we don't really care about this 120. That's part of the host field. What we care about is that third octet, and we care about which subnet is 67 in. Well, since this is what the third octet subnet mask looks like, 224, the rightmost bit of that subnet mask is in the 32 field. So that means that when this subnetting was done, it was incrementing the subnets by 32s. So the first subnet was 9.12.0.0. The next one was 9.12.32.0. Next is 9.12.64.0. And then 9.12.96.0. Okay, so those are the only ones that we need to put down here because they cover our .67. So which of these networks does this 91267 fall in? Yeah, falls in this one. So that's our network address. So again, you always, whenever you have your slash number, turn it into your subnet mask, or you don't even have to. You could just say, I know that the first 2 octets are 255, 255. I only care about the weird octet. And then just put however many bits down in your table to come up with the 17th, 18th, and 19th bit. And then we only care about that rightmost one to figure out what our subnet increments are. So our subnet increments are 32, 64 is one of them. So 67 is inside the 64 network. So we're 9. Dang it. Buttons on these. Click. 64.0. All right, now the broadcast address. So the broadcast address, it gets a little bit more interesting. So 9.12.64, 64, and this is again a good time to put everything in binary, or not everything, but what you need in binary. So 64 in that third octet looks like 0, 0, 1, 0. Okay, and then the rest is host. Right? Because we only have, 19 bits are the network ID, so it only goes to here. That's our delimiter. So 64 looks like this, 0, 1, 0, and then we don't care about the host bits right now. So, well, we do care about them because we want to figure out the broadcast address. So the definition of a broadcast is all the host bits are
Ones.
binary 1. So let's just write, here's our network ID. These are host bits in the third octet. And then the last octet is all host bits. So I don't even need to put the binary down. It's gonna be what?
255.
255, right? Because that'd be all binary ones. So all we have to do is figure out what's the value of this field, the third octet. So we just plug this in, 010 is 64, and then this is the 16, so that's 80, 88, 92, 94, 95. So the last two octets will be 95, 255 for our broadcast. It'll be 9.12.95.255. And again, you could have gotten the 95 by looking at this and saying subtract 1 from that. You just got to remember to make the last octet all 255s. You know, all ones to make it 55. Okay. So hopefully that gives you, you know, most of what you need for the quiz that's coming up this, that you have to finish by this Sunday. This table is also in Canvas. Let me bring up Canvas here. And I'll add, I think. So the solutions files are not yet available. Well, you know, I'll make them available because you're not turning them in, so I might as well make. But I would say if you're at all still hazy on, you know, IP address, also there's IP addressing practice problems. This was also a worksheet that I hope you covered in CNT 101, where it's asking you based on the class of address, what part is the host, what part is the network, which addresses are valid, which are not valid, things like that. But anyway, the solutions files are all there. I'll have to do it for for both classes, unfortunately, so I got to remember to do it. Which class was this? I just did it. This was for the Zoom class. I just did it for, so I'll do it for the C class as soon as we're done here. So the binary conversion is the only one I don't have the solution file for. I've got it for the binary hexadecimal and the IP addressing. Or there should be oh, I know that subnetting one I didn't put up. I'll put the subnetting worksheet up here, the one that I just had on the board up here with the solutions as well. That way you can do them, hopefully check your work. And if you can do all of these worksheets, then quiz is coming up this week. Should be really fun. All right, like I said, I have to go to a conference this Wednesday, Thursday, and Friday, so I won't be here Wednesday, but we're doing the Module 2 labs. And like I said, there's only a couple, shouldn't take too long. There's 2 groups of people. So, you know, if you should have time if you need to ask Brendan for some subnetting help if you still need it. I'll get those additional worksheets put up here so that you got them. All right, we'll see you next week then, next Monday.